I don't know how many of you basically try to train a transformer on something tiny or just started to do this via the API. So has someone ever trained a transformer on? Okay, but okay, either some are shy or some never tried and then you've done it via the API. So you'll get a chance to do so today and slightly work with it. And then I will show you a little bit how the transformers work with what are the new developments in transformers. Then Adrian will join and talk to you about his work on trying to speed up inference with transformers, so stuff which is basically here and now that they are doing to improve them practically right now. So this first part will be more about what's in the future. This is what's happening right now, and then you will have a moment to play with it yourself and have me and Marek and possibly Adrian remotely to help you with things. And hopefully this will be a fun morning. So AI is hyped. Yesterday, Sanjeev asked me whether there is still hype for the LLMs, and I told him, well, LLM is AI right now, and this is well, it's a Google Street View screenshot from when you are driving through the Bay Area, because there are places where basically it's, you would think this is already over, but it's even more hyped. So basically, if you drive through Bay Area, so if you start somewhere in Menlo Park or Palo Alto from Facebook and then Google and all the way to downtown San Francisco where OpenAI is, you would have billboards basically speaking about AI in all tenses and what an AI will do, and it's only getting crazier. And you also note that there were several awards for AI. So it's already at 2 Turing prizes, right? Because there was one for Hinton and LeCun and Bengio, and then recently there was one for Sutton and Barton for RL, and they are 2 Nobel prizes and a few minor prizes awarded to it. So there is something definitely happening, and a question is, why now? Because when I was 2, the DARPA tried to do a self-driving car. And the funny thing about the self-driving car is that it had many features that this Waymo car has. So the Waymo has a couple of cameras, and this guy also had a camera. It was actually, I guess, this thing here, which required some cooling by the time. And the Waymo has a computer, and this also had a computer, and this is much of the space in the back. And the Waymo has a deep neural net, and this guy also had a neural net, which is the funny thing, because this was a moment when people believed that neural nets will work. So it was running a deep neural net. And the question is, what happened in between? So why the AI hype is now and not basically in the 80s, when people had pretty much exactly the same idea? So let's take a robot or a car and stick cameras to it and add a computer to it and add a deep neural net to it and have it figure out how to drive itself. And by the way, this car was driving. So it was able to drive, I guess, up to 40 miles per hour and negotiate some intersections and so on. So it wasn't a total failure. It just wasn't as great as people hoped. So any idea what changed? Yeah. Pretty much this. So the sad part is that what really changed is the amount of compute and data, and the algorithms change slightly. So I don't want to say there is nothing new in neural nets since the 90s, because there are a couple of ideas to make them work, but the blueprints for what will work was already there. And in a sense, this is the bitter lesson that Richard Sutton said, and he's the recipient of the Turing Award for reinforcement learning, that if he looks back at the 70 years of AR research, the methods which win are the methods which can harness hardware. So basically, if you want to have, and the way I want you to read it is basically to have impact, you have to align with the way the wind blows, basically. And in AI, the wind is blowing in the direction where the hardware will take you. So his main idea was there is nothing that will beat Moore's law. There is an economic initiative for the Moore law to be true. So the amount of compute is growing. And if you have methods which can ingest this compute, then you will be a winner. Maybe not now like the Alvin car, because it had too little compute, but in the end, the methods are there. So the idea was there. They were the pioneers of of this. And then, of course, it's a Jelinek memorial workshop, so you have to quote Jelinek, I guess. So his famous quote, every time I fire a linguist, the performance of the speech recognizer goes up. But this was also a moment where people tried to employ methods based on statistics of speech and text corpuses for translation, rather than try to derive rules. So basically, ultimately, what works right now, so methods which scale with the data and compute, as opposed to methods which scale with our idea of how the world works. And quite boringly, the three pillars of AI that we have is algorithm, data, and compute. And you pretty much have to have the three. So we wouldn't have the AI craze without compute, because it was required to train. We wouldn't have it without the algorithms, because while the deep neural nets were known, we needed to make them scale to basically the size that we have right now. And then we needed to have the data. So if someone magically gave the Alvin guys the algorithms and compute, there still wouldn't be the data on the internet that we joyfully put over the last decade. And these are the three pillars, and there are also the three things which at some point will start limiting what we can do with it. Because if we run out of either of them, so if there is a problem with the algorithm, or a problem with the data, or a problem with the compute, we will need to find out something to basically grow the structure higher. So for a very high-level overview, these are the three things that people are looking at. And for the algorithms, like a very, very brief introduction, the power horse right now is the deep artificial neural net. So it's very, very roughly brain-inspired. In the brains, we have those cells called neurons. The simplest and crudest mathematical model you can make of them, right, is that you take a weighted sum of the inputs and threshold it. And when it's larger than a threshold, you basically emit a signal. And when it's smaller, you do nothing. By itself, a neuron cannot do too much. And it's definitely not something that you can scale, compute and data and do more stuff. But if you assemble them into a network, so this network is composed of those tiny things which do very simple operations, then basically magic happens, and suddenly you can show inputs to it and ask questions, and this thing starts to learn. And we like them basically because it's a system of many, many equations and even more variables. So if every data sample is an equation, then every parameter of this network is a variable, and you can always grow it larger. So in this sense, it scales with the amount of data, even though it looks like it's a function. And theoretically, you can use it to feed basically any input-output relationship. And those guys work in parallel, which means that basically they make very good use of hardware which is right now parallelized. So if the network was organized in a different way, like in a huge circle, let's say, and it would be all sequential, then we would have something which can fit anything, but doesn't scale with hardware. And instead, this is very easy to parallelize. And there is a hypothesis by basically Łańcucki that if you do a large enough neural net, he had this hypothesis 10 years back, so let's say that this is vindicated already, then success is guaranteed. And his reasoning went like that. We do have a large brain, but the neurons in the brain are kind of slow. So they are firing at 100 hertz. Definitely not what the CPU is doing with gigahertz. And we have a pretty good reflex, because we can react to stuff under 1 second, which is a feat having a 100 hertz processor. Because you cannot do too many basically sequential operations to take any decision. And this is somewhat optimal, because we have it, the animals have it. And the very quick characterization, like fight or flight, so whether you want to engage something or run away, this happens really, really fast. So if it's 0.1 second and you can have a neuron fire 100 times per second, then basically it's like you can have 10 of them in a row. Maybe more, but this order of magnitude. And then his hypothesis is whatever we can do without thinking too much, then a deep neural network should do. And basically, success is guaranteed. It's powerful, trainable, universal. And this is, in a sense, pretty scary, because like, if you think about, say, driving cars, I don't say you should do it, but if you think it's possible to drive a car while talking to someone and respond to, I don't know, text messages on your phone, this means that you don't spend too much brain power on it. It purely runs on this instinct. So it cannot do too many, back and forths through what you are thinking through. So this should be amenable to a large enough neural net, just because the brain wouldn't be able to do it in the background, like while focusing on other things, with the way the neurons in the brain work. So it has to be basically a reflex. And this tends to be true because all of the things related with perception, so computer vision right now runs on deep neural nets. Speech recognition right now, in a large part, runs on neural nets. So this is definitely true for perception. And the term that we are using right now for it, it's scaling laws. So AI wanted to have a Moore law of its own, and this is a picture from the OpenAI paper on scaling laws, which basically says, if you have a measure of quality, here this is a validation perplexity, and you start taking larger and larger models, which is basically the color on this plot, and you train them for longer and longer, then this thing converges on a doubly logarithmic scale. So the only remaining problem is basically money, because every step here it's a 10x of what you've invested, but basically you take the small models, they saturate at some point, and basically this is not working well. But you take exactly the same model, but make it larger, and suddenly it becomes much better. And this is the, let's say, the OpenAI speech to investors. So if you give us money, we will take you from here to here, and we will see in a moment what those levels can mean. But this is basically the correct AI researcher, stack more layers and grow things as opposed to engineer things, because with scale, stuff will work better. More is different. So we've talked a tiny bit about compute, and now the remaining part of the puzzle, and this is, let's say, the GPT hypothesis, is that data and next word prediction is all you need. And we'll try to do a little experiment to show you what I mean by that. So we'll do a guessing game, because everyone likes it. So you will be telling me what could go into those 3 dots. Good, you can say good. White, yeah. Okay. Mari took a milk bottle out of the fridge. The milk is cold. All right. So the distribution shifted quite a lot, right? It's still good and it's still white, but it's not the most interesting thing. She took a bottle out of a broken fridge. Now the milk is warm, or yeah. She forgot to put the milk in the fridge yesterday. The next day the milk is, yeah, soured. And now the point is, this is a very simple task. It's language modeling, but see how much knowledge about the world you have to be good at this modeling task, and how intuitive this is. So you not only have to, like, the milk is white, is probably a trigram model, right? Something like that. So you could totally do it with basically very, very simple language modeling. But the idea that the milk is not white, but let's say soured, because it was in a broken fridge, or because it was not in the fridge overnight, this requires some knowledge about the world. So at this point, you can say that we are beyond statistical modeling, or maybe not beyond, but even if all we do is statistical modeling of text, we are really building a world model. Because we are infusing the computer with knowledge that milk is something that can spoil and is usually white, that fridges are stuff which, if you put things into it, it's cold, but broken fridges actually don't work, so it's warm. So at this point, you really need to do properly at this game, you need to know quite a lot about the world. And the beauty of it is if you have the data on the internet, you don't have to work how to represent this knowledge into the computer. So there were many attempts by people to engineer a way of knowledge representation. So they were the semantic web approach. There was a project called Psych, which tried to formalize knowledge. And in a sense, all of this is irrelevant the moment you have an algorithm which scales. So if you take a large enough model, you will get a good performance on this task, and if you have enough data. Because suddenly the models learns all of those little intricacies about the world which are really, really hard to codify. And this basically puts a meaning to those scaling laws. Because you can say, okay, the perplexity here, maybe it's unigrams. So the letters come with proper frequency, and it's useful in a few places. You can break simple ciphers with it, so the simple language models work. And then at some point, maybe you get the words right, or paragraphs. But then if you really push it to the limits, to do really well on the next word prediction, you start to be needing common sense and state tracking and in context learning, because all of this is in the text, right? The dream would be you say to the computer, is P equal to NP, and then it will come up to you with a proof. So it will generate new knowledge. But all of this, in a sense, goes through language. And the powerful statement they did basically is that if this keeps on scaling, and this is from 2005, so it's from 10 years back, then basically with every 10x we will be getting something which is better. And this is why they were saying, okay, we have GPT-3, which is somewhere here, right? But you know, the GPT-7 is going to be way, way, way below, and this is going to be truly intelligent. So they started to basically measure the intelligence in those orders of magnitude. And this is and now the question is what's next. So if I told you, and basically there are three frontiers which in a sense start to be seen because the scaling wallows were taken to their limits. So the first question is where do we get the data to feed this, to feed those models? Because it turns out that internet is a finite quantity basically. Then the second one is how do we expand the knowledge that the models have, or basically take them from interpolation. So if I have seen enough text about milk, I know what milk is, to new things. And the third one would be about coherence, which is basically, if you want the models to do something agentic, if you want the models to be on their own, they have to be resilient to the errors they make, as opposed to they have to be good at predicting the continuation of a path that someone else made to them. And this is very different, to follow someone else's reasoning than to do on your own. So let's start with the data. There was a report actually updated a year ago, which said that we are good until 2028 because this is the amount of data the language models use, and roughly the stock of data, so how much of text we are putting on the internet is this green line. So it turns out that basically OpenAI and so on are so good at raising money that they were able to eat all of the internet sort of by last year, which basically explains why the GPT-5 turned into GPT 4.5 and why Llama has problem releasing the large language model, the Llama 4 Behemoth and so on. Because at some point, we've used all of the useful text data on the internet, or at least the big labs did. So the story about GPT 4.5 is that it's basically started to overfit on epoch number 2. It's so large and so well at memorizing stuff that they were able to do 2 passes over the internet data. They were hoping for more because I guess that the GPT-3 and so on, they did around 10. So we are pretty much out of data. And this is one of those 3 pillars, right, which suddenly hit a ceiling. And we'll have to find a way around it. And one thing the labs are doing right now is multimodal, because we have run out of text, but if you think about the videos, it's way more, and they teach you something about the world. So this is, it lacks VO3, so this is not the state of the art right now, but it's basically, you can try to look at it and see how much of the models know about interacting with the real world. So if it were a robot, can it use, say, this model to predict the outcome of its actions? And I wouldn't trust the Sora one. It looks okay, but it's subtly wrong and in a painful way. But basically, it's a way to harness more information about the world. So it's a way to build a better world model, because right now we are not only talking about it, we are predicting what's going to happen. And this is a very fruitful research area, especially in robotics. I guess the approach, which is the most research right now, is not even just generation, but trying to figure out what was the action and then predict the outcome. So try to learn counterfactuals together with this. And robotics will be a huge benefactor of it, if we are able to predict what's going to happen. And this is something we do as humans, because we are predicting what we will experience through the senses in a moment. So we definitely do a conditional world model with what we are going to see and hear based on what we and the others will do. And the funny thing is that if you do those representations with deep nets, you can actually try to align them. So it's called the Platonic representation hypothesis, and this basically says that if you try to map between representations learned by models on different modalities or on different data, you can pretty much align it in the latent space, which really means that they are learning representations rooted in the data. Like the models are large, but in the end, the data shines through them, and you can map this together. So it's very synergistic to do this multimodal training. Okay. So the data frontier, I guess, will eat all of YouTube, right, and so on. For text data, there will be a problem, and I want to show you right now a little bit of what people try to do with the lack of text data. And this starts with this realization that a little bit of self-reflection, so this chain of thought prompting, gives better results. So when you allow the language model to generate a few words before answering, it's usually better. This is the early chain of thought approach, where you would basically show in the prompt examples of how to think. This later on reduced to basically explain to me step by step, and the model has seen enough of textbooks to understand what step by step means. But the main idea is, rather than outputting an answer right away, so intuitively, you allow the model to do a few steps of reasoning. And then this improves the result. And if you try to train the model to do it, you are basically in a different world, because now you are playing a reasoning game, which is the reinforcement learning models. And the gist of it is, you pose a question, you ask the model to generate several of those reasoning chains. So not only one and then you take the answer, but you do several of them. And then you score them and promote the best ones. And the details are beyond what I will be able to teach you today. So for the details, you will have to go to the RL papers. But all of the RL methods basically boil down to this step. You have to generate lots of trajectories with a model, choose the best ones, and somehow upweight them in a training step. And if you think about it, the prize are the better reasonings. So this really, you can say, okay, it's a reinforcement learning training. There is nothing new in the sense, but no, you are left with the reasoning traces, and they are different than, say, proofs that we put on the internet, because they are the raw search through a problem space, as opposed to the cleaned up version that we use to present it to ourselves that the models were exposed to in the training data. Now, the trick, of course, is that you have to be able to score and promote the best reasoning. So you have to have a way to judge whether something is correct or not. And this is the caveat in these approaches. But it works when you can do it. And this is basically the basis of OpenAI 01, and then the O3 and the DeepSeek models and so on. So this is an active area, mainly because it allows to spend compute on the RL training and fight a little bit the data problem, which right now is acute because there is no way to get more from it. And the models basically, if you ask them to show the chain of thought, this is from the OpenAI blog post, they start to reason. So they would say, what's going on here? We are given, I have a hypothesis, let's verify it, wait, this doesn't work. So it looks like you are going through basically a trace of an algorithm browsing a search tree. So pretty much what classical AI was about, how to search in problem spaces, but now everything happens through tokens. And this opened a third way of scaling, which is basically test time training or search. And we probably will reuse everything we did for search in AI. So we had alpha beta pruning and so on. We had Monte Carlo tree search more recently to beat Go. Because this basically allows us to burn compute and get better results and have the data sets along the way. So this generates new data to train new models, and there will be lots of research on it. But the caveat is basically coming up with good functions, and this is a very hard question. if you wanted to promote intelligent behavior, how would you reduce it to a number or some scoring function such that you can take the non-intelligent traces, separate them from the intelligent ones, and come up with the best ones? And people that do human management know that there is something called the Goodhart law, and that this basically kicks you every time you try to formalize something. And this is Goodhart law working on RL in Atari game playing. If you remember, there was DeepMind which started to do those Atari games as a way to basically learn intelligent behaviors. And the models usually were trained to maximize the score in the game. And here the model figured out that it's a racing game, and you see that there is this race going on here with the other balls basically going towards the finish line. But this guy here found out that you can get partial points for burning stuff, and there is this one loop where you can grab the fuel and burn those ships, and grab the fuel and burn those ships, and it gives you a steady stream of points. The score is here in the, you see here the score. So it's maximizing what it's being trained for. But this is not the intelligent behavior we are we are craving. So a similar thing can happen basically with those reasoning models, unless we have a proper definition of intelligence. They will maximize whatever we are training them for. If you are training them for basically tricky reasonings, they will give us tricky reasonings. If you are training them for some sort of math, they will do this math and learn all the shortcuts that are in the data set, basically. But it's really hard to generalize beyond it because it overfits to the task in a weird way. Okay. And then the third pillar of what I think is going to happen, where is the cursor? The third behavior, frontier that we will start to be hitting also with the reward models is basically the coherent behavior frontier. This is a projection from, I don't know, startup or foundation in the US, and they tried to plot a scaling law for how much you can do with AI versus humans. So the scale here is basically how long they estimated it would take for humans to do a certain task. So this is not the runtime of a language model, it's more or less a pricing of a task in terms of amount of human effort. So there are things that we do very fast, like answer a question to which we know the answer, and this is the 15-second. We can do small algorithms like count words or search the web and find proper web pages, but then you can also do more complex stuff, and somehow they try to measure it by training models, which is maybe not the best task that human can do in 4 hours. You can take quite a substantial decision in 4 hours. But then they tried to plot basically how good the models do on those tasks, and came up with a claim that the length of the task is doubling every 7 months. So this is like another Moore's law, but this time for scaling of what the models can do coherently. And this is the other axis that basically will have to be maximized. And this is the one, in a sense, more interesting algorithmically, because this is the only one which touches on how the models operate. Like the data, it's not how the models operate. You just get larger models and then fit it to them. The reasoning one, it's another way to train the model, whereas here, perhaps this will require us to rethink how the models work, because they also have the bottlenecks in terms of how much coherent they can be. In the end, the transformer is an autoregressive language modeling tool, and it has a context window, so it sees a chunk of the past and doesn't see more. So if you just run out of it, it will start to forget. But there will be more for this coherent behavior, especially if you think what will happen not when you go to things that we can do in 4 hours, but to things that people can do in a lifetime. Like you have people with a lifetime goal of something, mathematicians which want to tackle a particular hypothesis throughout their lifetime. And this is what we would say, this is the peak of human intelligence, and this is very, very different than doing a few web searches in terms of complexity and how we approach it. And in a sense, the problems that we will have, it's first of all, we will need to have models with extremely long context, perhaps infinitely long context, so they never forget stuff. and they internalize what they have seen. So basically, whenever they discover something, they can reapply it in other places. So somehow the conclusions they draw while doing inference, they have to be internalized, and right now these are two separate mechanisms. The inference is inference, the model is frozen, the training is training, and the inference is minimal because the model is trained on the correct traces. There may be some degree of recurrency required, for sure. Maybe it will be the verbalized thought, so the chain of thought. Maybe the recurrence through discrete tokens and text will be basically too limiting. So we have this idea that you sleep over a problem and brain does something fuzzy and you come up with it the next day and you know the answer. So maybe we do something like a mean field approximation rather than this sampling of very concrete results, and this will require the models to operate in a different space. So not in the space of verbalized things, but in the space of those vectors and way fuzzier. And this is something that the transformer is not doing right now. We probably will need to have continual learning. So when someone works on a problem for a long time, they are changed. When they work on this problem, they learn new things, even though they didn't reach a solution, right? In a sense, the reward is the journey. So we cannot expect a model to tackle, I don't know, a week-long task and solve it using the same model. The model has to change. It has to change because it has to learn what it was doing. So, so it will require, I don't know, we spoke about it yesterday with Sanjeev. I don't know whether we will change the transformer or whether we'll figure out a way to hack it into the transformer by doing algorithmic things to it and have it basically super inefficient. But it will have to have the behavior of basically remembering more of what it came up during inference. The inference and training have to blend in order to tackle those large tasks. Then of course, we have the problem of basically doing all of this in a trial and error fashion, as opposed to predict the next word after a correct prefix. Just like when you learn to drive and someone is there to take the wheel all the time, everything is funny. But the moment you make a mistake, you go from this good road to this bad road, everything is different. And the language models also have it, right? So they are trained on the data which is curated, cleaned, and then you put some noise into them and they respond with noise, or you ask them to do a long reasoning and they get lost in it. Okay. So this is my zoomed out view of what will be interesting or what will have impact. And now, because the first two things like data are perhaps best left to people that deal with it, and you are probably more interested about the algorithm and how you can change by changing the model, or at least I am. I wanted to show you a little bit what's happening with the architecture itself. So where is the in-context learning happening with transformers, and then how you can make them more recurrent, and what's right on the horizon in terms of it. So very quickly, let's go over what's the operation of the transformer, because we will want you to change them during today's practicals, so the last hour of the tutorial. So a transformer, it's a large neural network with a very special operating mechanism that basically it processes sequences, and every token of those sequences mixes information from the other tokens. You can mix everything from the past when you generate, or you can mix stuff in parallel. So it's a very good model to ingest data which is sequential, and when you're mixing information from several steps. And we train them on language modeling. You now know why language modeling is a good training task. The first way to think about it is that basically it's just an autoregressive language model. So we are having a context, which is the blue part. We are having a word which we are predicting, which is the orange part. And there is something called the context window that we will use to predict the next word. And we have a very powerful mechanism of mixing stuff in this context window. So how a transformer looks like in more detail with code, because I will want you to change this code. So first of all, the properties of it, it's parallelized across time, because basically you can process all of this context independently. It's deep, it's residual, there is an L missing. So typically it's composed of several blocks which are the same. It interleaves mixing information from the past, so this attention with the feed-forward network, so basically the stored knowledge. So you can think of it that the transformer is basically a loop of several iterations of, let's look into what I have at hand, with the task at hand, so let's look what's in my context, and let's look what I've learned in the past. Combine the two, let's take another look at what I'm doing. And you can scale it in basically 3 ways. So you can scale the depth, how many layers, so this one has 6, but you could put 60 into it, and that's easy. It scales with width, so how many neurons, especially in the feed-forward, so basically how large is the network, and it scales with time, so how large is the context window. And the nice property of it that it's the amount of compute is pretty much the product of the 3. So you can have a longer time and then smaller depth, and it's the same compute. In code, basically, it's pretty simple. You start with some token embeddings, then you are looping over the blocks and doing predictions. So it's a deep net. The block in and out of itself, it's attention and MLP. I want you to show the code because then you will have the code and you will perhaps have a little understanding what to change. And there is really nothing really strange happening here, right? The main thing which happens in the MLP is that it's always up projecting and down projecting. And this turns out to be important for basically the performance of this model. So it's a generic 2-layer neural net, but it always does, let's split this information, see what happens, and then project it back, so this sort of shape. And I'm telling you this because people tried to reproduce whatever the transformer is doing, especially Seb Hochreiter's group tried to see what was wrong with the LSTM, which I guess it was the main recurrent neural architecture and language model and using speech recognition, and they were like, okay, so there is this transformer, and why the LSTM is so bad? So they took a vanilla multi-layer LSTM and tried to train it, and it was really bad on language modeling. But then they basically added the ResNet and the transformer backbone, so basically this idea that you have the time mixing and then the MLP, and the MLP does up projection and down projection. So pretty much everything, but replace the masked multi-head attention with the LSTM block. And it turns out that this is a dramatic reduction of complexity. So maybe it looks very trivial that the neural net shouldn't be like this, Christmas tree shape. You start with something wide, and then it gets smaller and smaller and smaller until you arrive at the conclusion. No, it's this expand, contract, expand, contract, expand, contract shape. But this is what drives a lot of the difference with what people were trying in the past. So basically a tiny insight. And then basically there is how you mix information from the past, which is also important to get the final bit of the performance. But this drop is huge just for getting the proper shape of the network. The remaining secret sauce of the transformer is the mask self-attention mechanism. So basically we take our input, right? We try to expand every token into 3 parts, so the query, key, and value. And then we are matching all the keys to all the queries and taking a weighted average of the values. So we access the past in the sense as a memory which is content addressable. We come up with the keys and values, and it's masked because we shouldn't peek into the future. It's really easy to do modeling when you don't do it. So in math, right, formalized, you take a vector, you project it 3 times to obtain the query, key, and value. Then you compute some sort of similarity between the keys and queries. It can be a dot product, it can be something more complex. We take the dot product right now basically because it's really fast. And there is this trade-off of how smart your model is versus how fast you can iterate it. So simplicity here is good. And then you basically take a weighted average. So you normalize the scores, take a weighted average, and everything works. To make it slightly better, you can do it several times. So you don't do one query into the past, you do several ones. And all of this improves, but the main idea is every past token can send you 1 key value pair, and you can retrieve it at will. The remaining technical detail is how you don't get lost in the order of things in the past, and there is something called positional embeddings. So you embed, you say to each token, you are this location or that, or you basically rotate everything a little bit, and this is what works right now, the rotary embedding. So every key and every query is slightly rotated. For the signal processing guys, this really looks like a IIR filter where you rotate stuff in the complex plane, and then you look at the real part. And in a sense, that's it. So the mask self-attention that you will be changing today, it's basically do the projections, apply the positional embeddings, match the keys and the values, and read out the result. And the magic is that this starts to have those new properties, namely this in-context learning, when you try to apply it to very large tasks. So if you ask yourself the question, what can be learned by transformers? So what can be learned by language modeling? Well, you can say, obviously it can model language, but can it model something like algorithms? So for instance, what if you are starting to ask the model questions about arithmetic and so on? Like, would you bet an n-gram model would do it? So is it something better than the n-grams, and if yes, in which sense? And of course, if you do short addition with a large model, it will work. But the interesting question is, what happens if you take large models and then large algorithmic problems? So what happens if you do basically long addition? So you train the model on what is 2 plus 2, what is 22 plus 22, what is 222 plus 222, and so on and so forth. And then you evaluate it on even something larger. So you say, okay, it's, I really want this attention mechanism and so on to generalize to longer sequences. And suddenly, you don't say, my model is a fixed size circuit. I have those layers and I can do computation with 20 steps. I have a program. It's a weird program because it's a program which takes many parallel steps, but maybe I can do more with it. Maybe I can write my program using the prompt and then execute it on something else. And it turns out the answer is yes. One way to look at it is that if you squint your eyes between what the two-layer MLP computes, so half of the transformer does this, take a vector, multiply by a matrix, apply nonlinearity, multiply by another matrix. The other half does this, take a vector, multiply by key and query and do the dot product, apply a nonlinearity softmax and multiply by another vector. So they look pretty much the same if you squint your eyes, give or take that the nonlinearity is different, and one is trained and the other one is derived from the context. But in a sense, you could say the attention is not just a way to access information from the past, it's a way to create a bespoke, a one-off neural net that will solve the problem of the next token prediction. So seen like that, the transformer is basically something which learns, it was sometimes called the fast weight programmer. So it learns the weights that will be used to solve just the next token. And then for the next token, you will learn another set of weights. And this is really cool. And for instance, people started to do it just this. So just to show you how long you can stretch this idea, there is something called TAP PFN, where they said, well, let's do a transformer to learn classifiers for normal data. So let's basically have a model. You take all your training data set, concatenate this into pairs, X and Y, feed it into the context of a transformer, especially trained on it, and then give the transformer a couple of test points and ask it to basically categorize those test points using the weights derived from the cache. And it turns out it works. The main question, if you read the paper, the main question is how do you generate enough of basically fake tabular data to train it? So they came up with a way of generating fake data which looks like the data people would normally apply, gradient boosting to and so on. And this is very competitive with XGBoost and so on, while being really fast because there is no real learning here. It's just you apply the transformer, you put your training data set in the context, you put your questions at the end of the context and it answers them. So this is the power of this in-context learning and what sort of moves this architecture away from just memorizing the previous tokens. And there is also some research which says, okay, if we know this can implement algorithms, what can be implemented with it? And for instance, you can prove that a small transformer will do gradient descent on some virtual weight that it's maintaining in the KV cache, so throughout the inference. That there is really some learning happening when you show it a problem in the context and then ask for an answer. But the other approach that people had to understand it, and this is important, right, to scale the transformer is, okay, if it's doing learning, if it's implementing programs, then what could those programs be? And I want to show you just a little highlight of a basically Python-like programming language which can be used to implement what the transformer is doing over the context. So the hypothesis is, if the transformer can basically learn to generalize on algorithmic tasks or on this tabular learning task, then it's really implementing a program. And if there is a program, we should be able to write this program in a way that we understand. And people came up with the idea of this RASP-L, which is the Restricted Access Sequence Processing Language. It looks like Python, and I know that I will go very fast through it, so you will feel like you understand. I also feel like I understand, but it's extremely tricky to program in it. So, so basically, it's a couple of functions. The X here, it's always an array. So all of those functions execute over all of the history that the transformer is seeing at any point. So you can take some tokens and map them through a function. You can take two sequences, zip them together and map them through a function. You can generate indices. So this is what this rope embedding we're doing in the transformer. You can reset your signal to something. You can compute how many matches you have. You can do attention. So you can do, you can match to a predictor and select one output. And it looks like Python. The trick is that you always work over a sequence. And you can try to figure out how to write a RASP program to solve a task. So for instance, here the task is you are given two numbers, and you have to basically output a sequence from the first number to the second number. So your data set is always start of sequence, then a set of numbers, then an end of sequence, then something else. And this is the KV cache of the transformer or the input tokens. So there is some junk, and then there is the start of sequence, and then there is the desired input, and then there is the desired output. But remember, the transformer is really doing one step ahead prediction, so we can think about what it will be doing for each of those tokens. And the program can go like, okay, let's find the starting index. So we make a sequence of the starting symbol with values as indices. We are trying to match it, and then take the last place we have seen it. So basically, we do a query into our key value store. Give me the last time you've seen a start of sequence token. And you get a sequence of zeros because there was no start of sequence, and then 2 because the start of sequence was at position 2. And then you do, let's take what's at location starting index +1 and starting index +2. And suddenly and this is executed in parallel for all the steps, so it's super tricky. But it gets you the starting number and the ending number, so it's a 1 and a 4. And then you can try to write down, okay, so take the last number I've emitted, add 1 to it. So it starts to output a sequence of numbers, then compare it to the ending number, emit an end of sequence token. And this little RASP program, if you execute it on a sequence, will give you basically proper next token prediction. So I don't want to go over too much detail over it because it took me a moment to figure out how it works, because it's really tricky to read with the amount of parallelism that's going inside of it. But the very neat result of the paper was that if you can write a RASP program, then most of the time you will be able to train a transformer to solve the task. So there is really a correspondence between what we can express in this language and what the transformer is doing, which sheds some light over what computations are possible, which would also later on tell us, well, to what it will generalize. And we can also try to think, okay, is intelligent thinking or is, searching for solutions amenable to programming in this language? So I don't know, is beam search amenable in Raspberry? Is Monte Carlo tree search amenable in Raspberry? Because this will limit what the transformer will be doing when it's trying to solve a large task, because this is the reasoning it can do. If the hypothesis that basically transformers learn what Raspberry programs you can write, and basically the paper showed two things. If there is a Rasp program, the transformer will learn it. If there is no Rasp program, then it's really hard, or properly stated, if the graded students that were doing this couldn't come up with a Rasp program, then the transformer usually failed. Yes?
In this case, they were having the loss of this Rasp program to train it, or it was somehow figuring it out itself?
Excuse me?
So it was somehow figuring out itself, this Rasp program, or they had training data on this one?
So they came up with algorithmic tasks. They were trying to write Raspberry programs for them. And then what they found out is that if they were able to basically write a Raspberry program, you could train the transformer on data generated for this task and it would generalize. If they couldn't write a Raspberry program, then usually the transformer couldn't generalize. So it's a way to say we have a somewhat convincing argument that Raspberry captures what the transformer is doing and it's not too lossy. Like if you would have Raspberry programs that work and transformer cannot learn, this would say that Raspberry is too powerful. And if it were the opposite, you could say where Raspberry misses something and the transformer will do more. But the alignment was pretty good. So basically this is, if you think about expanding what the transformer is doing, this is a starting point to understand what formally it could be doing in those ways. So it's more than just remembering the past, but maybe not that much more. So to summarize the transformer, right, we really like it because it super aligns to the hardware. The Raspberry is good and so on, but the reality is that it's an architecture made for the current hardware. It's very powerful, so you can fit it to pretty much any data you want, and as long as you have data, like Ilya Sutskever said, success is guaranteed. But it also has some problems, like the lag recurrence, which we know is important for even very simple things. They have this fixed size context window that people try to improve. They have all the other problems, and maybe there are solutions around them that would basically take us out of this limited set of programs they can learn. And I want to go really fast right now through some approaches that are happening right now to expand transformers with recurrence, which is one way of very promising, one very promising research direction. So during training, transformer parallelizes across time. What do I mean by this? You can execute the layers one by one starting from the bottom. And this is because of the special connectivity that it has. This is really nice because you can do stuff really fast on the parallel hardware. And then you predict the tokens also in parallel. But during sampling, you have to run the whole stack from bottom up all the way up to the top, get the sample, feed it back, run the second token, feed it back, run the third token, feed it back. So sampling is always sequential. And we have to maintain this historical state of the transformer and use all of it to make the next word prediction. And the question would be, if during inference this thing is sequential and recurrent, shouldn't we use this recurrence during training as well? Because recurrence is more powerful than just the autoregressive behavior. So basically, it's for signal processing guys, it's the difference between FIR and IRR filters. You can do more with less if you do an IRR filter, even though it's tricky. And so we have already seen one way of the recurrence, this chain of thought. It's really a recurrent transformer, and theoretically, it's actually a huge change when you do no chain of thought or chain of thought, because no chain of thought is this Raspberry word of programs, so very limited set of concepts that you can learn. Chain of thought is Turing complete. So you add this little bit of recurrence, and suddenly you are in a very different compute paradigm, but it's really tricky to train. The other question was, well, can we just loop the past states, so do the recurrence inside of the transformer? And it turns out, yes, you can, but it's slow. So you have better results, but you are fighting Moore's law in a sense. You are fighting with parallelism. So doing this is actually beneficial. And the question people are asking right now is, can we have something which is both fast and recurrent? And it turns out that there is a sweet spot that everyone tries to do right now, which is the cumulative sum. So the cumulative sum, it's a computation which is very simple. It's recurrent because you can rewrite it like that. So you have a state, and you are adding stuff to this state. And it's fast because you can do this cumulative sum in all of logarithm of the n parallel steps. And this is the, in case you are wondering how it happens, this is the circuit to do it. So you are adding stuff in pairs and then pairs of pairs and so on and so forth. So doing a parallel sum, it's easy, but to have a prefix sum, you also have to add what's missing, and this is the second half of it. But this seems to be a good trade-off between I am recurrent, and during inference I am recurrent. During training, I am not totally parallel across time. I do have to pay this logarithmic penalty, but the logarithmic penalty is not a problem. A linear penalty in time, yes, this is a problem. I have to do my steps one after the other, but the logarithm doesn't grow too fast, right? So this is an okay, basically, trade-off. And you can do it for something more generalized than just a summation. You can basically do this for a field of operations. So mathematically, you need to have a generalized multiplication and a generalized addition. So this would generalize to everything that we were also generalizing other things like the weighted transducers in Caldi, right? So every field could be used for this as well. So this can work. You could basically have matrix multiplication and addition as long as this is associative and commutative stuff works. The addition has to be commutative. And the idea, again, has been in the making for a while. So this predates the transformer. There was something called, there was the LSTM, there was the convolution net, and there was something called quasi-RNN, which tried to basically do the gates, then a cumulative sum over them, and then pulling of the operation. And it was waiting for its moment. So now it's called a state space model. And it's everywhere. So first of all, the transformer can be changed to be recurrent. So the transformer does this. It computes the similarity between keys and values, queries and keys. You could make this similarity, which right now it's exponent of the dot product. You could change it instead into just the pure dot product. And if you remove the nonlinearity, if you do it perhaps expanding the dimensionality, but you just do a pure dot product, you can rewrite it in a way that the query is pulled before the sum and you have some state here. So this doesn't seem like much, but in this formulation, you really have to loop over all the past to do a match. And here you can put all of the past into a matrix. It's a sum, right? So you can implement it using a cumulative sum during training. You can implement it using a sum during inference. It's a form of recurrence. And it actually works as long as you try to upscale the dimensionality here. So you cannot do it in a small dimensional space, but it works well in a large dimensional space. And it's a way to take a transformer and make it more recurrent. So the cumulative sum is there, and this is a model that people are exploring. Actually, we do have a model like that at Pathway, and it's really competitive with the transformer as long as you do properly the up projection here. It's large, it's sparse, it's quite smart. So if you want to know more, please talk with me. But there are other contenders to the transformer that people are exploring right now, like, I don't know, this RWKV, which has this time mixing. And if you read the paper, there is lots going on. There is some gating, there is convolutions, but the crucial part is this time mixing. And if you look properly what they do, there is this sum over time with some multiplications, and you implement it using a cumulative sum. Then there is the XLSTM that I was telling you. They were trying to reconstruct the transformer. And again, the core of the XLSTM is a cumulative sum over something more complex. So there is the exponential gate, But the crucial part is we do the cumulative sum, which is just enough to give us a recurrent flavor, but then little enough to still be parallel during training. So I hope that we will get to the point that you will try to implement this today. This is the part of the practical. Exchange the softmax attention to this dot product attention, see that it works, or try to make it work better because it requires a few tricks. But this basically allows you to have a model which is recurrent, and especially on the smaller scale, whatever 10 billion means. It was in small scale a while ago. Those models are competitive with the transformer while being basically faster during inference. And give the idea that, okay, we are now recurrent, we have this infinite memory. Whether the model will learn to use it or no, it's a different question, but it doesn't have this basically cutoff threshold that the transformer would have in and out of itself. Or you don't pay that much for history because they learn to basically compress history into a fixed size. So this is the current active research in the alternative of transformer. All of this tries to be both parallel and recurrent, and pretty much a million ways to do a cumulative sum in these guys. But now Adrian will tell you what you can do more directly to a transformer to compress its memory. So if you say, okay, the transformer has this KV cache, it's large, but maybe it cannot be it doesn't have to be that large. But because Adrian is joining remotely, I'll just ask him a question okay, so Adrian is on Zoom. So I'll just ping him. Yes, if you have questions, please ask me. And if someone could help me with switching to the Zoom, it would be perfect moment for it. Yes.
Maybe I missed it, but correctly I missed it. You mentioned somewhere at the beginning that it would be desirable to learn during inference. Did you ever get into it, or is it in the future?
So the question was, I said it will be desirable to learn
right.
To learn during inference, and did we get to it? So so the answer is partially. So I maybe didn't make the point too well, but if the in-context learning works, in the sense that you can, for instance, like the stub PFN was working, so you can put a data set into your prefix, and then the transformer will answer correctly based on it, then in a sense, learning may be proper chunking and storing of the history. And then we would say the proportions have to change. So right now, the model has weights. The weights are large. They're actually extremely large. They are pretty much just as large as the amount of data that went into it, give or take a factor of 10. The KV cache, it's also large, but it's small at the beginning. And it's basically discarded every time. But if you inverted the proportions, if the model started small, and the KV cache could be large or growing or expanding, then maybe all of the learning could happen in context, which is one way to address this problem, maybe the most magical way, because we would say we will just scale the models with the larger KV cache and it will all work. But this is in a sense the dream. So if you have the state space models and you say the model will be small but the space will be large, and at some point everything you know is in the space. So everything you've learned is in the history that you've seen. This may not be enough, though. There may be a need to some more direct transfer of this. You could, of course, do gradient descent when you are just doing inference, but this is called fine-tuning, and basically it's tricky to do properly. I didn't put it on the slides, but there are also ways to try to formalize building of the state of the model as some sort of learning. Basically, because all you do, especially in those state space models like linear transformer, you have a matrix and you're adding a outer product into it. if you train a model with gradient descent, whatever you put in your weights is an outer product of the error signal and the input. So this is very similar, and people have reformalized the linear transformer as a way of basically doing gradient descent on a training signal during inference. So this is getting intertangled. Yes, there's another question.
So let's do this. There's a Victor Zoo method, which is if you have a question, you raise your hand. If you have a question that relates to something that's being talked about right now and you don't want to wait, you raise 2 hands.
Okay, that's perfect.
So you can go next if you like, unless you have an immediate question.
I just wanted to ask about the restricted access sequence programming language. What is it about that architecture that allows you to like generalize transformers? Like what is it that it shares with transformers that allows you to do that?
So Raspel is an attempt to formalize what could the transformer do. So they tried to formalize what the MLPs are doing and what the attention is doing, and basically come up with a set of functions that you could implement in a normal programming language that would do stuff that the transformer could be trained to do. So the main relationship is if we say that maybe I didn't do this argument from a high level enough perspective, but what I wanted to say is if modeling of text is a proper task to learn a world model and so on, and you can do crazy complex stuff with text because all of the human knowledge is exchanged via text in some form. Maybe text with images, but basically pretty much this. We learn to distill all of our knowledge into books, and this is what we give to the future generations to understand how stuff works. So in this sense, learning on text is really powerful. And if you think that you can put questions and reasoning and so on into textual form, then this modeling of text is also modeling how to reason and how to do algorithms and so on. So in this sense, the question was, well, is the transformer like a better n-gram model? And some people have argued this. So okay, you have this attention, you can match to a prefix, but maybe you know a transformer is like a skip-gram model. An n-gram is you have to take n consecutive words and it's somewhat limited, and all the transformer is doing is basically takes a word and then a star and a word and a star and so on. And it's a machine to extracting this kind of statistics. Does it work for language modeling? Well, yes, it will be better than n-grams, and n-grams are pretty good, especially if you do them at scale. Does it reason? It's hard to say that the n-gram language model is reasoning really. So they try to formalize what the transformer is doing and show, well, look, it implements an algorithm. If it implements an algorithm, it's doing more than just matching patterns, because an algorithm can be search, for instance. So the connection here is it's a formalization of what the model is doing. You can try to either come up with how to write your reasoning procedure in this formalism. So for instance, or how to expand it. So if you say, I would want the transformer to do something like Monte Carlo tree search over the KV cache, what would it take for me to change? What I would need to add? And Raspel is a starting point in it.
So thank you for the great talk. Yeah, like the associative scan can improve the time complexity to the log n, and it's a sequence length with a tree-like structure. But how about the spatial complexity during the training time? Does it make sense? During the inference, the recurrent structure will definitely reduce the spatial complexity compared with KV cache, in my understanding. But how about the training time?
So during training, if you implement the transformer naively, you have to keep all of the KV cache as well. Because basically you have to compute it, and then you have to reuse it when you do backpropagation. You can do things like basically you partially forget it and then recompute. It's called checkpointing. So you can try to minimize the memory footprint by, first of all, not storing all of it for the backward pass, but recomputing parts of it. Mm-hmm. And you can also do pretty much the truncated backpropagation through time. So what you can do is basically you take part of the last KV cache from, say, the last mini batch, and you append the fresh KV cache to it, and then you keep the old one as a read-only thing. It's called the Transformer Excel, and it actually works. It allows you to expand the field of view of the transformer without having to keep all of this in memory for backrow. But basically, this is but the size of the KV cache is a problem, and Adrian will.
Okay, so even during the training time, the transformers training spatial complexity is harmed by the KV cache, and
yes.
associative scan will helpful even during the training.
Oh, yes, yes, yes.
Okay, good. Thank you so much for
It is,
clarification.
and well, it's a problem, and that's why NVIDIA is doing those huge memory on basically graphic cards. In a sense, for training is not that bad because it's still more compute bound than memory bound, but the two has to increase hand in hand. For inference, it's even more. So I would say both use lots of memory, but training is able to parallelize better and uses more compute for the same sequence length. So training goes faster because basically you can parallelize, and it's roughly equal in terms of memory bound and compute bound, whereas inference, as Adrian will say in a moment, inference is more memory bound than compute bound.
I see. Thanks so
So
much.
you don't have basically enough stuff to do for a parallel processor because it's sequential. I'll just write to Adrian what's happening.
Yeah, so this RASP-L stuff is new to me. I had not seen it before. And I was trying to, I'm going to read more about it later, but I was trying to think about how to think about it. Should I think of it as like, in the Chomsky hierarchy sort of way, meaning it's a more expressive way of describing what's being done with strings? Or should I think of it more in the computational way, meaning it's not quite Turing machine, but it has more. So what's a good way to think about it at a high level? When like I said, I didn't fully grasp it, so I'm going to read more. But how should I approach that
I guess
topic?
I would be thinking, I was thinking about it in the second way.
In the computational way, okay.
In the computational way.
Okay.
So basically, it's not a Turing complete language.
Yeah.
It's not a language where basically you can only work with input of size, up to
Right.
the depth or something like that. And you get a better sense of what the trade-off. But
Okay.
honestly, it's really tricky to wrap your mind about what's computable.
Okay.
Because it's a small step of extremely parallel computations.
I see. Okay.
There was a lot of research in distributed computing on algorithms which do some exchange of information. Though the transformer is slightly different because there is way more communication than the other
Right.
paradigms. So it's.
Yeah. Okay.
But I would say it's a way to formalize the set of languages that it can
Okay.
recognize.
All right. Thanks. Any other questions? Okay. Right. By the way, we do have a full 3-hour block, but at some point, if you want to take a short break, you can do that too. I'll let you guys decide how you do it. So, we think we should do a 5-minute break? Okay. So Hamza says let's do a 5-minute.
Let's do a 5-minute break.
Bio break, and
Okay.
then we can continue with Adrian. Right.
And a lot of my great contributors. And I sort of structured the presentation in 3 main parts. First, I'm going to discuss in a little bit more detail the paradigm of inference time scaling. Jan kind of showed that in a couple of his slides. I'll try to make it a little more deeper. Then I'm going to tell you about those two papers, two algorithms that we have developed, and then close with the result of the second paper, which kind of combines inference time scaling with KV cache compression into this new paradigm, which we call hyperscaling. All right, so this is the NVIDIA CEO, Jensen Huang, at CES this year. You can clearly see that the test time scaling or the reasoning paradigm is getting more interesting, and it draws more and more attention. Just to fill in, like what we call here pre-trained scaling is just scaling the model in a pre-training. Then post-training is something that we had around, I guess, for the past 2 years. I would put into this bucket fine-tuning of models or RLHF. And right now we're in this reasoning scaling paradigm when you try to squeeze more accuracy from the model by just scaling the reasoning. Now, what I mean by scaling the reasoning, there are two, like the simplest ways to go about this. First one is sequential scaling, when you try to just increase the length of the reasoning chain. So not only just chain of thought prompting, but also trying to extend it by making the model either to discover how it can learn on its own, or trying to officially increase the length of the reasoning chain. The other one is parallel scaling, when you try to develop a couple of reasoning threads in parallel and then somehow reconcile them, just summarize them into a common answer. And then, of course, you can think about hybrid approach when you can combine these two. So you have longer chains, but also have a few of them until you arrive at the final answer. Now, this is something that Jan also had on his slides. So it has been recently discovered that at least until some point, you have like a fairly linear, clean trend when you prolong your reasoning chain. So you generate more and more tokens, and then you increase the accuracy on reasoning tasks. And now this kind of looks like you can make this assumption that the more tokens that you generate, the more compute you need to invest. It looks like there's this assumption that you are limited by the number of generated tokens. And why would that be the case? The problem is that during inference, autoregressive inference in transformers, you are memory bound. So you can look at the plot on the right. This is measured in a very simple scenario, not really a server inference kind of scenario, but like a simple framework inference scenario, bFloat 16, Megatron LM, which is like a training framework, but it doesn't matter. You can see that until a certain step, you pay the same latency for every generation step, but around 16K of tokens, it starts to go up. Now it starts to go up because your KV cache has become very large, and then the cost of just reading that KV cache from memory dominates or just starts to dominate the entire cost of every inference step. And now we can see that the longer the reasoning chain that you generate, it becomes more and more costly. Now, just to try to fill in a couple of details here, let's take a step back and think about why is that the case? So during generation, the cost of attention is linear with respect to the sequence length. It's not quadratic like during training. It's linear just because you get one query vector because you're generating a single one, and you need to make a dot product with all the keys and all the values, which is length L here. So you really need to just multiply one query by all the keys and all the values. Now, maybe let's look at the two plots on the bottom right. Here, there's just latency captured for a single layer from Llama 2, 7B. On the left, you got a feed-forward module, so MLP layer. On the right, you got self-attention. And until you retrieve, until the cost of retrieving the weights or parameters or activations from memory or KV cache from memory is higher than the actual computation that you do, you're going to be memory bound. And you can see that MLP is kind of memory bound in this model until batch size 128. After 128, you can see the latency goes up. And this is the case because you're paying more for calculating, doing the actual matrix multiplication than for retrieving the weights for that matrix. Until batch size 128, you really don't pay much more for increasing the batch size, at least for the MLP layer, just because you paid more to retrieve the weights from the memory. On the right, you can see something similar, but for self-attention, and it's just linear. For self-attention, you will always pay regardless of the batch size, just because for every sequence in the batch, you have a separate KV cache, so the costs scale linearly. And on the top right, you have an excerpt from the specs of H100 SXM. So you can clearly see that the 16-bit maths are like at least 2 orders more expensive latency-wise. 2 orders faster than the memory bandwidth. So in order to be fast, you gotta just limit the amount of weights or KV cache that you are reading from memory. If you cannot do it, you're gonna be memory bound. And then on the bottom left, there's a graph showing with Llama 2, 7B, how much memory in 16-bit precision do model weights take, and it's a blue color. And then in orange, you have how much memory does KV cache take with batch size 32. And then when you get to sequence length about 4K, you're actually at the limit of the capacity of 80 gig GPU. Now this got better with recent generations of models just because they have GQA, but you can see still that this gets you fairly limited. And now the question would be, where can you make savings on KV cache? So here is like a simple graphic that shows you like the main dimensions of the KV cache. What can you do here? You can try to reduce the number of heads. That's what GQA does. Maybe you can apply some pruning to the model, but you're not going to get so far until you start losing accuracy. Now, the hidden dimension, you can apply sparsity. You can also apply pruning. Again, not going to get you that far. With batch size, you can share KV cache when you get a lot of sequences that share, for instance, the same very long prompt. So you're going to ask a lot of questions about the code base, and then in the prefill phase, you process the entire code base, which is like this big old prompt. Maybe you can share then some KV cache in between layers, but as soon as you start generating, the paths are going to diverge. So the best bet here, when you can make more savings, is trying to compress or reduce the sequence length. By the way, there are 2 dimensions here that are not plotted. One is quantization, of course. You can quantize KV cache. Again, there's a ceiling that you're going to hit pretty soon. The other one is you can actually try sharing KV cache in between layers, which is like yet another dimension you cannot see here. So now for a moment, assume that we could compress KV cache 8 times. Assume there is like a magical method that can achieve that. And let's think about what will happen. So here are 2 projections made for Qwen 2.57b. I've made those for Qwen just because we have results later on for this model, especially for the reasoning variant of this model. Now on the left, there's a plot where I assume that the baseline model is not changed, and then I assume that I have like this new magical model that has 8 times smaller KV cache. And now we can see that if I just change the batch size in that new magical model, I can either reduce latency or increase throughput. Just because I've got more memory. Essentially, I have reduced KV cache 8 times, so I can increase batch size 8 times and then still fill the same memory that I had before. And now by changing the batch size, I can traverse this new Pareto frontiers, which is kind of different for different lengths of generated sequences. Well, because the latency, as you could see like 2 or 3 slides ago, changes with sequence length, right? Once you become really memory bound. And on the right, it's a similar plot, but now I assume that the baseline model also changes batch size. So I change batch size in both of them. And you can see that if I scale batch size in both of the models, you get more latency drop. Essentially, if you would have higher batch size in the vanilla model with long sequences, that would kill you just for reading the KV cache from memory. And then compressing KV cache 8 times really saves you a little latency. So there are savings to be made here. The savings are the higher, the more tokens you would like to generate, so the more inference scaling you would like to do. Now, there's a lot of very clever methods that are training free that can sparsify KV cache or try to compress KV cache. We don't have time to go into details, but I would like to show you just those 2 plots from a recent paper by one of my co-authors. Actually, 2 of my co-authors. They have been exploring the limits of train-free KV cache sparsification, and they have been trying that with different methods on different tasks. Now here on those both plots, every dot is a separate task. And then on the y-axis, crucially, you get how much compression you can apply without losing substantial accuracy. And well, they found that there's many tasks when you can go as high with KV cache compression as 10, 15, or even 20. But unfortunately, there is a lot of tasks when you really cannot go far. You have a lot of dots here on this plot around like 2 or 3 KV cache compression, which is, it's okay because it's still nice optimization, but it's not that substantial. We would like to go for much higher compression if it would be available. So now I'm going to show you our first method of KV cache compression. We have published that last year. It's going to be a baseline, which we're going to improve with our second method. Now, the interesting thing about this method is you can go much further with compression once you allow to train the model to compress. And before I explain how to do this, I'm going to first show you how it works in inference, because that's kind of easier to see, and then I can build towards how you can achieve that to training. So in vanilla transformer, KV cache management is fairly easy. Every new key value pair that you generate, you append to the KV cache, so it's just a list, and that's all. In our method, we thought that we could try to change this to an online behavior in which the model decides whether it would like to append a key value pair to the KV cache or try to compress it by averaging with the last element. So I'm going to show you how it unfolds in time. The time is this vertical axis here. The model predicts a binary decision variable, alpha, and then we have chosen that alpha, if it's 1, then you're going to accumulate KV tokens to the KV cache. If it's 0, you're going to append it. So here I keep on accumulating. Predicted alpha is 0, then I'm appending. And you can see that the KV cache, if you are accumulating, it doesn't grow. So if you are appending only 1 steps out of 4, you're gonna compress KV cache about 4 times doing so, and the model can learn that. And then, like I said, we accumulate through averaging. So we always just modify the last token on the KV cache. And we treat keys and values separately with the same algorithm and the same weights and the same kind of averaging. Now, alpha are predicted by the model. We just borrow 1 neuron or just 1 dimension from the key vector, normalize it to 0, 1 with logistic sigmoid, and then round it to the nearest integer. Weights go through kind of similar treatment without rounding. And then we have devised those formula for averaging. Now, these are recurrent, so you just, like I said, you average with the last element. Crucially, those formula can be implemented with associative parallel scan. So this is kind of very, very simple realization of something that Jan has showed on his last slides. So in other words, you can apply fairly effective, and it matters during training, fairly effective left to right compression or averaging of such sequences in log n or log L, where L is the sequence length steps. Yeah, so during training, we relax those decision variables to be continuous on the interval from 0 to 1. In order to do that, we sample alphas from gamble sigmoid. So we kind of have a sigmoid with a little bit of gamble noise here. Crucially, we do not prune away any tokens. We need to keep all tokens in the sequence. And we do this because we would like to have some intermediate states. So training deep models that make discrete decisions is super hard just because of non-differentiability. And now we're trying to make some intermediate steps that the model can visit, which have some sense, some meaning. Now, on the right, you can see how the sequence would look like if you would keep averaging. This is unfolded in time. Now, when you interleave averaging with appending, from time to time, you just like reset the state and then keep averaging all over again. Now, when you go for relaxed alphas or relaxed averaging weights, this amounts to like partial averaging. And when we train the model like that, the model kind of learns to do it, but then it's interestingly decides to prefer either alphas that are 0 or 1, just because alphas that are somewhere in the middle are really unstable and they just affect the loss. So the model naturally gravitates towards having binary alphas, which is kind of interesting as well. Technically, in order to like fully achieve that during training, we plug in 2 places. So we do this relaxed left to right pooling on keys and values just before running the actual attention, but we also need to devise a special mask. This mask is super important, and it's hard to see at the first glance, but I hope we'll get there. So during inference, you always see, during inference, when you keep averaging, you always see like the last averaged representation of the average tokens. Yeah, right. When you have averaged like 2 tokens and you average third one into them, you no longer see the version with 2 tokens. In other words, during training, you need to have all the intermediate steps unfolded, but you need to block access of the attention to the steps that would, during inference, get overwritten. And this is sort of shown here by those grayish arrows. Like Q5, query 5, shouldn't be able to attend to those partial states because during inference, those states would not be there. They would get overwritten. And we need to kind of simulate this with this attention mask. We have resorted to a additive attention mask. And because it's additive, we can mask or not mask or partially mask a token. And we kind of translate the alpha decision variable to a masking value. And this is, of course, end-to-end trainable and learnable. And so using those both elements in green boxes, you can tweak the attention layer to accumulate this new way of doing attention that allows you to do partial accumulations. And now the most important thing is that you can actually initialize this algorithm in a way that at the beginning of training, it is doing only appending. So you're adding like a bias to the decision variable that the model needs to overcome that bias in order to just start to accumulate anything. And it really helps because in order to actually have a very large language model and really try carefully not to break it, and then also try to teach it new behavior, we believe that you need to go extremely carefully in small increments. You cannot just enable this this algorithm abruptly because you risk destroying the model. And you can see that as the iteration of training go. And by the way, we just compare with the GQA that in the original paper, when you would like to apply it to a pre-trained model that was not trained with GQA, they proposed like this uptraining procedure when you just, like I said, kind of break the model and then try to fix it through additional training, which they call uptraining. So in our way of training, which we, by the way, call retrofitting, so it would differentiate from like this break and then reassemble kind of thinking. You can keep the loss fairly stable and then introduce the compression step by step until you reach the desired amount of compression. And now this algorithm applied to vanilla Llama 2.7b with 8 times compression, now measured in a real model, really allows you to traverse that Pareto frontier that I told you earlier about. So you can either choose to decrease latency or to increase throughput by increasing batch size. And this latency stays flat for a while until it goes up, even though you are increasing batch size, just because this is the point where you have paid already the price for retrieving the weights of the model from the memory, and you also memory bound the little compute that you add by increasing batch size. And by the way, this is with like smallish sequence length. Yeah, it really doesn't translate to increased latency. And then some evals. Maybe I'm not going to spend too much time here, but I can try to convince you that like 4 times compression on the downstream tasks that we have tried really didn't bring any degradation. And we have observed small drops or maybe manageable drops around 6 times to 8 times compression. And here we compare with H2O and TOVA, which are train-free methods. Interesting thing is that you can actually look at the compression patterns because we learn a different compression pattern for every attention head. And as we train, the model starts to develop this very interesting pattern where different heads in different layers compress more or compress less. And you can see that in the first early layers of the model prefers to have full resolution of the sequence and really doesn't want to compress at all. Then as you pass like half of the model, you can compress fairly a lot. And then towards the end of the model, it really prefers to have just a couple of layers for resolution. And then the bulk, I would say, of KV cache needs to really be retained in the first half of the model. Here are similar plots for 2x, 4x compression on 13B model. And on the bottom, the interesting one is the 7EB, which was the first Llama model that featured GQA. So this is why you'd have only 8 heads, because the GQA heads are shared, 1 KV heads shared between a couple of query heads. Now, this algorithm, cool as it was, had one very large caveat, meaning that it was very fragile and expensive in training. It was still a lot cheaper than training a model from scratch, but again, amounted like to about 2% or more of the training time that you need to otherwise train from scratch, which is a lot and really not advisable in practice when you are trying to compare with train-free methods. And this is why we started working on something that would be much faster, which is dynamic memory sparsification. And now that we have covered a lot of groundwork, explanation of this should go much faster. So the mode of work is kind of similar. At every step, the model also will predict alpha, and that those alphas will be extracted in kind of similar way. But now the alphas control eviction, not averaging. So that's like the first substantial change. The other one is that we try to break the model thinking that is featured in train-free token eviction methods. Train-free token eviction methods try to evict low probable old tokens under the assumption that something that has been seen a long time ago, it's not going to be really attended to, especially if it keeps on collecting low attention scores. Our thinking is radically different. We are trying to evict very fresh tokens. So the model will notice that they are missing, and we hope to steer the model towards selecting those tokens that would otherwise, that could be evicted without any harm. And it turns out that such tokens exist, and there's a lot of them. And so the mode of operation is as follows. When a new token arrives, the model will emit a decision variable alpha. Now, depending on the alpha, the token will be marked for eviction, but the eviction would take place later on in a couple of steps. Because you evict a model in a few steps, this implicitly creates a sliding window behavior, right? The token is fresh. You say that every token marked for eviction when it was fresh is going to be evicted in 16 steps. So you get a sliding window of 16 tokens. And within that sliding window, you are guaranteed to have full resolution of KV cache. Like nothing gets evicted. And this is shown on the right. So the orange tokens are quote unquote marked for eviction. And as soon as they fall out of the sliding window, or if there's no sliding window, really you can think that after reaching a predefined number of steps, they're just being thrown away. Now during training, this is fairly similar mechanism to what we shown in DMC, because actually you can get away with programming that pattern just through attention mask that is additive. So you have probably the same mechanics. You build a additive attention mask that is based on a sequence of alphas, but now by design this attention mask encodes the sliding window and that delayed eviction mechanism that I showed you before. Now on the left is a binary mask. It's not really a training mask, but you can use a binary mask in the prefill phase of inference when you need to process a long sequence during one go. And on the right, there's a real valued mask that represents the same thing, but during training. And of course, there is no pooling, so there is no parallel associative scan, nothing like that. So the algorithm gets greatly simplified. Here, during training, you just need only that mask and the sampling of alphas. Now, when you compare the two side by side, and we did a fairly thorough comparison, with the new method, which is sparsification, DMS, you can achieve even higher compression rates. We get up to 12 with still high results on downstream tasks. Crucially, the training time is reduced 60-fold. And I should say at least 60-fold. We are still experimenting that, and probably it could be even shorter. So we can now train the model to compress 8 times in 700 steps, regular training steps or less. Now this is super interesting because it's not just faster. It's not that it's an optimization. Our belief is that it kind of shows that the information about if the token is useful to the model to calculate attention or not, that information was already encoded in the token. Like 700 steps, especially with such a tiny learning rate, it's nothing for this model. You cannot really shift it towards any new meaningful behavior. So 700 steps is barely enough to expose the information that was already in there, which for me is super interesting because I never thought that it would be the case. Now, when we look at applicability, we kind of started experimenting with this on the new generation of models that are reasoning. And this is where, in a second, that inference scaling paradigm is going to come into play. On the implementation side, maybe I'm not going to comment much, not to bore you guys, but I have 2 slides right up. So when you are discussing a lot of novel ideas, it's nice to discuss them as like those virtual mathematical objects, but we shouldn't be too much detached from implementation just because in order to those ideas become successful and have an impact, somebody would have to implement that and they gotta be working fast. Now, when you recall the compression patterns that I showed you before, they create this problem that KV cache is no longer this nice tensor that has a predictable shape, right? If every attention head has a different sequence length, this is going to be very wild in terms of the shape and doesn't really play nice in being stored in matrices. A easy solution here is to use page attention, which is used anyway by all inference frameworks, which sort of boils down the problem of KV cache allocation to chunking KV cache into pages, and then you can have a block of those pages, and then you can reuse them as you generate new sequences and then drop the old ones. And when you get variable sequence length for every head, you can just have 1 page for every head. And in our experience, it doesn't introduce, at least in our setups, any meaningful delays. In the future, it is possible that dedicated solutions are going to be adopted. And now I know for a fact that NVIDIA has developed something that is called KV Block Manager, which is supposed to abstract away KV cache management from the framework and then be like plug and play and then expose a clean interface for the inference framework to interact with the KV cache. So what I'm saying is that there is a possible future in which inference frameworks like VLLM or SGLang or TRT-LLM all use like this highly developed and optimized KV cache manager that once you implement your ideas or anything you need to have inside that KV Cache Manager, all the frameworks can benefit. Just because KV Cache management gets more and more complex. Now, during prefill, when you get that kind of weird mask that I showed you before, you might be thinking that maybe it's not really worth it because a lot of problems like coding assistants need to have optimized prefill phases, and maybe it's not worth it to go for unoptimized prefill phase and use a different method. Now, it turns out that something like this has been already developed by Baidu, and then a framework or modification of flash attention called flash mask has been developed, and it allows you to not only mask, but skip computation in the mask parts of the attention with a range of different attention patterns. And it turns out that we kind of fit into one of those patterns. Another interesting thing is that reading papers on sliding window and then KV cache optimization, attention optimization, the numbers for sliding window size that we are familiar with are going to be more in thousands of tokens, like sliding window of 1K, 2K, 4K, or 8K, something like that. This is common in the literature. In our case, we can get away with sliding window of only 16 tokens, and the model worked pretty well. And the largest window we have tested was 256. I'm pretty sure we could go for more, but it was something that kind of like saturated when we are trying the sliding window size. We have also tried to do not delayed eviction, but do immediate eviction. This is kind of similar, but you extract the decision variable from the current token when you are deciding to evict the token that has just fallen out of the sliding window. And the results degraded a lot, as you can see on those plots. Immediate eviction is the eviction that you right now extract the decision variable about the past token. And this is like another indication that the information whether the token is going to be useful or not to calculate attention is inside that token. If you would like to decide with a new token, which technically should have more information because it's more recent, it should know better if the old token is interesting or not. This is not gonna work that well. Here I'm showing you just small ablation again on the window size when you go for higher compression on the Llama 3.2 1B instruct. Crucially, this is a very fragile model, like 1B model that was, I think it was made by distillation from the larger one, especially instruct tuned. Those kind of models are very, very fragile to additional training. And somehow with our method, we are, and again, with a very low number of training steps, I'm pretty confident that we are not changing much the way the model works. Just really what I think is going on is we're finding the information about which tokens can be evicted and then throwing them out. And more evaluations on the Llama 3.1 8B on more tasks. Again, there's a slight variation, but the scores are fairly well preserved. Also, the scores on the two bottom rows, needle in a haystack and variable tracking, which are like these benchmarks for how well the model can access its context. Even when you apply 8 times compression, we score high in those benchmarks. Now, I would like to spend more time here because we really try to put into perspective how the design of models kind of evolved throughout the last 2 years. So what do we have here on this plot? On the x-axis, we got the logarithm of the number of active parameters in the model. On the y-axis, we got in a log scale the size of the KV cache when you are generating 32K tokens. it's calculated for 32K tokens because some models have some form of sliding window or Mamba model, or Mamba layers, sorry. So the size of KV cache doesn't scale perfectly with the length. There's a constant component to that for some of these models. And so going from the top, you have Llama 2.7b and Llama 2.13b, two models that didn't have GQA, so they are fairly high. Then somewhere in the middle, you got this emerging trend line of the models that do have GQA. And interestingly, you can see like Qwen 2.5 had less KV cache than Qwen 3, which I think is still susceptible, like the amount of KV cache that is assigned to different models is still susceptible to experimentation by the developers of these models. DeepSeek v3 has a kind of different kind of attention, which is MLA, which has like this latent vector. But again, if you sum over the entire size of KV cache, even though it's chopped into latent vectors, there's pretty a lot of that KV cache. And then Llama 4 and the Gemma 3 models are kind of interesting because in those models you have interleaved patterns of sliding window attention and then full global attention, just because the authors try to have less KV cache in those models just to escape the cost of inference. Then the dashed line here are our models that we have tried in the paper with applied 8 times compression. You can see like there's a substantial reduction even with respect to what you can achieve with GQA. Now I put here in the frame that, of course, you should take it with a grain of salt because, well, our method will degrade accuracy a little bit, but as you could see before, and you will see later in the results, the drops are not that substantial, and I'm pretty confident that it's still very sensible to apply that kind of compression. And maybe the last two interesting models here are Nemotron H models, which are hybrids of Mamba 2 layers with transformer layers. And only those transformer layers have KV cache. So even though there's like very little KV cache in those models, you can get exactly there with the plain transformer models, no SSM, no Mamba layers, but with short, clever eviction applied. And just to fill in what I said with details, so Gemma 3 actually had 5:1 ratio of local sliding window layers to full attention layers. Llama 4 has 3:1. Nemotron H has sort of 11. It kind of changes in between the sizes of the model. And from this point of view, you can take a look at the same patterns that I shown you for DMC, but for DMS, now those patterns have kind of different meaning because we are doing eviction. If you are doing eviction of like all the tokens, anything that you're left with is just a sliding window. So what I'm trying to say is that when you look at the compression plots, the heads that are like nearly white, they have been reduced to sliding window attention, period. The heads that are dark, that are 1 or close to 1, those have really not reduced, but have retained the full attention without any eviction. So you can see that, and by the way, those are sorted vertically. So within every layer, just for readability, I have put on top for every layer that has that compressed least and then compressed the most towards the top. You can clearly see that like this pattern emerges, that every couple of layers, those models kind of prefer to have full attention in at least one head. And then they would like to have like higher resolution somewhere past the middle of the model. And you can think about all those patterns as like trainable versions of what people are trying to design by hand by doing those interleaved patterns, like in Gemma or Llama. And lastly, another interesting phenomenon with that concerns both DMC and DMS is that, well, our training objective is that the model should, on average, when it's being trained with context size for 4K, 8K, 32K, depends on the model, but on average, it should compress it, say, like 8 times, if that's the goal of the training. Now, the conditional entropy of language kind of is smaller the more context you condition on. And it kind of shows because the model then chooses not to compress uniformly, depending on the sequence, but shorter sequences are compressed less. And then the longer sequences are actually compressed more. So during training, it would average out to like 8 times compression over the entire context. Now, this is actually beneficial because, well, like you can remember from the very first plots, it's actually the long context that gets more and more expensive. And this is where we actually compress even more than like the print number and the tables that we show you. All right, so we have covered 2 algorithms, dynamic memory compression and dynamic memory sparsification. And now I'm going to show you like this new way of thinking of ours that you can actually try to compress KV cache when you're doing inference time scaling, and then we can see how both of these apply to a model compared to just inference time scaling. In other sense, there is a third axis of optimization that we can unlock. It's not right now not the Pareto frontier of latency versus throughput, but it's latency, throughput, and additional accuracy that you can choose where you would like to go with additional budget that has been applied through KV cache compression. So we have devised a couple of experiments. This is the setup in which we are working. We took very popular benchmarks that concern mathematics. So there's like math questions. There's GPQA Diamond, which is like science questions, PhD level science, and there's coding, live code bench. We have 2 metrics in our experiments. First metric is we're summarizing all key value reads from the memory, just because we think it's a good proxy for what is like the actual runtime performance of the model. This might be kind of controversial, but it's the only, in our opinion, way to be fair comparing to methods that are train free like TOVA or H2O, in which you have like this large sliding window. And in principle, you never know how large the window should be when you are running the algorithm because you don't know in how many steps the model will arrive with an answer. So overshooting that window will give that model unfair advantage. Having too short of a window when you start might make the score worse. So we're kind of summing up all the tokens. So it's like taking an integral over how many reads you need to make from KV cache on course of the entire reasoning. And then peak tokens in KV cache, it's the second metric. You can think of this in terms of, hey, how many tokens I can generate before out of memory error. That's it. The less the peak tokens, the more sequences in parallel you can squeeze in onto your hardware. And well, the goal is to find like this better Pareto frontiers that look both at accuracy and then at the cost, which is expressed by those either KV memory reads or peak tokens in KV cache. And so here you can see 3 algorithms compared. And then every data point is a triplet. The first number is the context length, so it's sequential scaling. The second one is the number of samples, so it's parallel scaling. And then you can see the compression of either DMS or Quest, which is our baseline model here. And then, of course, vanilla doesn't apply any compression at all. And you've got the IME, which is like mathematic problems score on the y-axis. On the x-axis, you have cumulative KV cache reads. So then the less, it's like a good proxy for overall runtime of the algorithm, you can clearly see that DMS dominates the vanilla. And then for Quest, Quest can improve the scores by a lot. But by the way, Quest is like this method that can save you on KV cache reads. It doesn't evict, but can retrieve less. It has this issue that with GQA, the savings from this method are much more reduced. Now here we are comparing peak memory use, and here it would be unfair to compare with Quest because Quest doesn't affect anything. So we think that a good baseline state-of-art method is TOVA, which is like the token eviction method. And again, you can see that we are able to substantially move the Pareto frontier. And now we try to aggregate the results. There are more results in our paper, but this is what we arrived at. We test 3 reasoning models. These are Qwen models distilled from R1 DeepSeek R1 traces. So those are fairly strong reasoning models on the further size. And now we have consistent gains, which we kind of hand-wavy try to estimate how like the Pareto frontiers differ, not the individual points. We have consistent gains that go up to like 8 or 10 percentage points on those benchmarks, which are fairly a lot with respect to vanilla, considering the little cost of the method itself. And just to summarize and starting to close, with DMS and this hyperscaling approach, as you have seen, you can have fairly large gains, putting in fairly little. We have found that the combination of both parallel and sequential scaling is kind of like the most effective, with the bias being on sequential scaling. And I think this is something that Jan also underlined in his slides. So sequential scaling is generally dominant. Sometimes the parallel helps, which is kind of exposed by our Pareto fronts. And whatever training-free KV cache reduction method that we tested, it didn't work so well, the DMS. And we think that like the desiderata for good hyperscaling, so applying KV cache compression in order to unlock more inference time scaling, is that the KV cache compression method needs to be very robust. And we believe we are the first people to do it, so actually combine inference time scaling with KV cache successfully. So just to close, yeah, I think I said it already. Yeah, I think it's a good time to close. I'll take questions, although that might be technically challenging. So Jan, I rely on your help here.
All right. I'm not sure if this still works. If you have any questions to Adrian, I guess you have to tell them to me, and I will have to tell them to him due to how the setup works. I do see questions, so.
Hi. Do you think this method can directly work out of the box even for, say, multimodal LLMs such as, say, audio language models? Because you need a lot of grounding for the audio context so that you can answer the questions correctly.
So, Adrian, did you hear it on YouTube or?
I heard something, but I have not plugged in the YouTube, so in order to then hear myself back.
Okay, so if I understand correctly, the question is about multimodal models and how would it work for basically audio models with the memory compression?
Sorry, with what kind of models?
Audio.
Audio. Huh, that's interesting. I guess it would work even better, considering that Well, this kind of compression, either the averaging or eviction, really would help when you have. So we know that you get this understanding problem of segmenting audio because in a lot of chunks there's really no kind of new information, and I think that the tokens really also could have that information, whether they are relevant or not, whether there is a new information, so like the change in intonation or really a substantial change in anything encoded into the token. And we kind of thought about doing this for a lot of time, so devising something like this for speech models, there was just never too much bandwidth to do it. So I think it's super fruitful to try to do it.
Hi, thank you. This might be a bit of a basic question, but I noticed you had the heat map in the first paper on the one introducing the idea on dynamic compression, showing the pattern across layers. I was just interested, I think, I tried looking in the paper, but I think this is average across all tasks, right? I think it makes intuitive sense that you see more compression across later layers. But I just wanted to see if you saw something different across different domains, or if it's just a universal pattern, so that's why you just aggregated everything in that single heat map.
Yeah, I'm gonna need your help here.
So the question is, when you were doing the plots about how the compression happens across layers, right? So did you see any general patterns like about this, beyond the fact that the early layers tend to lose more, well, with the exception of the first, right?
It was more about if there was like variance across different tasks, because I think they, tested it across different domains, and the heat map only showed, I think, aggregation of everything.
So do you have the heat maps, but across tasks? So how task dependent is how the model is compressing memory?
Oh, that's an interesting question. So we haven't looked into this that deeply, but doing heat maps a couple of times for different tasks, turns out that they are fairly similar, and this is because, well, the model is trained to compress always at the same rate. So this is something that we actually would like to try. Piotr, one of my co-authors, is like the most sold on this idea that the compression should be very much context dependent. So we should affect the way of training in order to let the model like choose to maybe compress more, less interesting sequences, and then when it encounters interesting information or very varying sequence underneath, then maybe do not compress that much, and that should be enforced by design of the loss function, right? Our loss function always forces the model to do the same thing. So yeah, going back to question, yeah, the patterns are kind of similar, but I would say it's an artifact of the way of training, because on a slightly different note, there's a fun experiment that you can do, which is you can try to prune away KV heads, even without any training, and you can prune away KV heads that you can see that look very frequently at the very first token, which is called frequently attention sync. So if you think that looking frequently at attention sync is an indication whether the head is frequently used or not, and you will do that kind of exercise throughout the different tasks, like reasoning tasks, or just plain next prediction task on next token prediction task on simple text, then you will get very different very different patterns. And it turns out that there are the hardest downstream tasks that we have. Actually, if you plot that like a heat maps on how frequently the model looks at the attention sync, that will reveal that difficult tasks engage more heads. So something that you are asking for, I believe, is really in there. It just, our method it's not optimized for that case.
Thank you.
I hope that kind of answers the question.
Hi, thanks for the talk. I have 3 questions. So first one is, how do you deal with the positional embedding once you do the both method, the compression or the sparsity?
So
I understood sparsity, but not more than that.
What you do is a very technical question. What do you do about the positional embeddings after you sparsify?
Well, that's a good question. So maybe I do have a slide about this. Yeah, the next one, right after the finishing slide. So the easiest thing to do is you always keep positional embeddings applied to the tokens in the KV cache, which is sometimes not that trivial, but let's assume it is. It might be not trivial because with extreme quantization, you start to need the resolution that is in those positional embeddings because it's going to get corrupted, unlike 4-bit quantization. But let's assume that. Then like this very fun optimization is whenever you would like to evict a token, I mean, you always will append the new one. So instead of appending, and in that particular time step, if you are evicting, you just overwrite the token. So here, K5, instead of going like at the end of the list, it just overwrites K2, which should be evicted really at this time. And for this trick, in order to work, you need to have positional embeddings because otherwise you will just scramble the sequence.
Okay, thanks. I have the second question, and that is how difficult is to fine-tune it. So I guess that if you want to enforce the this compression or sparsity, there was the regularizer term. So how well does it work among different tasks? Do you really have to fine-tune it? Do you have to have some schedule to enforce that, or does it really work nicely, like with some set of the values?
Jan, can you help?
Yeah, so how easy or hard it is to fine-tune to arrive at the desired compression level?
Meaning like resource-wise or generally like stability of training-wise?
Yeah, like the stability and really like enforcing it to do something, or is it like really there is some nice set of the values for the regularizer that enforces it and for them it works nicely, or is it really just you have to find one special point where it works nicely and otherwise it doesn't work?
Some help?
I think you have to repeat it. He didn't hear it.
I'm afraid you would need to repeat it also.
I can come there and ask it.
Maybe just come here, it's a very specific question.
So you have there the regularizer. So my question was that if you like, let's say there is some lambda or something like that works as a regularizer for the sparsity, and does it really work nicely that you have some set of the values for which it works, or there would be just one point and maybe, I don't know, you have to, over the training, have some schedule over that and it works just like that, otherwise maybe it does not enforce anything, or would you see that it's somehow easy to use? That would be the...
Okay, I think I get it. By the way, I appreciate you coming to the stage. Maybe first comment on DMC, or maybe both of them. So we do have a schedule that is linear, and we introduce, I left out a lot of details in the paper. Sorry, a lot of details that are in the paper. We have a linear schedule with which we introduce the compression. So you can see like how the compression develops during training, because the model, like I said, it starts not compressing and then it compresses little bit by little bit until it achieves the full compression. So that's one thing. And with DMC, like the first method that was much more costly, it could have been a little bit fragile. With DMS, I think it's super robust. It's much more robust than I would expect, especially that we were able to train a whole lot of those Llama 1B instruct models, which Yeah, they're super fragile. I mean, just trying to zero out some neurons or do very simple modifications on them could lead to those models breaking soon. One of the reasons that it got so much robust is using logic distillation instead of language modeling laws. So logic distillation really helps because, well, you don't have the original training data and your data distribution is going to change because of that. For this particular 1B instruct model, we had to generate a little bit of instruct data, which was kind of trying to guess the format based on whatever was available online. From the evaluation kit released by Meta, because instruct models typically have like those custom prompts, especially smaller models or the more sensitive to the prompt format. And in general, I would say that by design, that kind of eviction with signing window is super robust to changing parameters of training, and I haven't seen really this breaking without any reason. And the first thing that might be fragile in this algorithm is the data part, and logic distillation really helps. I hope that shines a little bit of light in your question.
Yeah, thanks. And I would have maybe the last philosophical question, and that is, like, we have a transformer that have the quadratic complexity. We could have the recurrent network that would have the fixed constant complexity, if you think of that. And then we have these methods that you have. So if you think of it, one was just to merge with the last token, and the second one was actually to drop some tokens. But if you think of it, maybe as you were showing, you would want to keep more and more tokens, but maybe you don't want to merge it with the last tokens. Did you also think about that you would not have there the Gumbel sigmoid, but Gumbel softmax, and you would be able to merge with any other token in the sequence rather than just the last one? Thank you.
Yeah, I mean, so it's a question of adding more expressivity to that mechanism, and well, the both methods are like fairly simple to picture and very simple to implement during inference, just because it's not that we don't want to go for more expressivity. It's because if you are going to do more, especially concerning earlier tokens in the KV cache, then you're going to pay the latency price. I mean, in order to not to increase the latency over the baseline transformer, it has to be super simple. Now, otherwise, well, you compress 8 times, but you kind of lose latency because you need to do more stuff to the KV cache. My personal understanding of this is that it's obviously not optimal, and then the optimal way to treat KV cache, like expressivity or the difficulty of training wise, it's somewhere else. And I guess it's yet to be found. An interesting, and maybe even more interesting set of methods would be devised for training from scratch. But because this is so expensive, like literally nobody really researches that. Only DeepSeek has something that is called NSA that is like proven, or at least in some scale, to work well, to compress training from scratch. Our method, I don't know really if it worked training from scratch, just because when the model is not converged at all, you don't really know when to drop tokens. And I have no idea whether that would train towards the same solution or as good a solution as applying this after training.
Cool. We have 10 more minutes, or I don't know how much. So one sorry, Adrian, to interrupt the QA session, but we need to find out what to do. So I guess the practicals, well, it's homework. The good news is that you are all accepted to use Lightning AI, so there are some instructions. We can really quickly try to get you started, and you do it later on, or I don't know, at night. It's JSALT, so we should be working 24/7 anyhow.
We can run maybe like 20 or 25 more minutes.
Okay, if that's just perfect. That's just perfect. So we'll try to get you started with this.
Let's try to finish at 9:30.
Okay, that's perfect then. Yeah, we both tried with Adrian to squeeze some more information, and I guess it was interesting. Thanks, Adrian. I guess you do see some common themes between what I was trying to show you and what Adrian is doing. So first of all, the bottleneck right now is on the amount of information that the models are generating during the runtime, and what we do about it. And you can try to engineer it more, so basically put algorithms like Adrian is doing, or algorithms plus a little bit of learning. You can try to say this is a model which learns to manage the state space because it's a recurrent net, and let the model figure out what to keep over time. There is a tension between doing this compression and just brute forcing it, because it's easier to learn when you brute force it. So I guess this is what was happening in Adrian's experiments to train the models from scratch. Like if you learn the models from scratch to compress, they will be very good at compression because they don't see the value of history. So they learn to throw it away very fast, and they only learn to throw it away selectively once they see the value of it. But it's a problem that to see the value of something happening in the past, you have to remember it. So there is this trade-off between how much you prune and how much you remember. And to be fair, the state space models are also not a panacea. Like you will not beat basically Shannon bounds. You have to store the information somewhere. You can store it into a matrix that the model is managing, then the matrix has to be huge. You can store it in the KV cache, then the KV cache has to be merged and somehow grow. And I believe that in the future, this will basically start being part of proper training of the model. So the KV cache and weights will start to be treated as one in the sense that both of them store parts of what the model is doing. And at some point, you could probably distill the KV cache in a very long-running task. You could probably distill the KV cache into weights and clip it. And especially if you think about those tasks that the computer will work for, I don't know, a week. It doesn't make sense at the time scale of answering queries within seconds. But if you think that the models should do tasks that we spend months, and they should also spend months, which is a thing to think about what will happen in, say, a decade, then probably some retraining and compression and very different things will be affordable because you will be able to do this, let's call it sleep time. Deep optimization where nothing happens, but then the model is somewhat better. So that would be the conclusion. The more practical conclusion for me and Adrian is that we are all looking for interns. So we promise not to steal you throughout the summer. But if after the summer you want to do something, reach out to me or reach out to Adrian. You have the emails, I guess. Or you can find us on LinkedIn or to Marek, who will be also looking for interns. Marek was more for the practical exercise. So basically, you are more than welcome to work with us on those topics. And if you need, then please reach out to us. And now we can try to transition to this, well, I even had a QR code with sign up, but let's say that we go to the lab QR code. And if I understand correctly, you are all unblocked for the Lightning AI Studio. There is a repository with, I'll just find the proper, I'll just try to find all the instructions.
All right, so meanwhile, I'm gonna drop.
Okay, so thanks a
Thanks
lot,
for the
Adrian.
invite. Yeah. Have a great summer school, everybody.
Okay. If there is more questions, I'll ping you on the phone if you have more stuff to answer.
Yeah, go ahead. I'm gonna be working remotely anyway.
Okay, thank you.
Cheers.
All right. So in the instructions, the reservations should work. Then there is the repository. It actually has a open in Studio, so it has a badge for the Lightning Studio. So if you are registered, if it works, Marek, did you send the invites to the common space? Did you invite the people or no? So
The thing is that all the emails and numbers you put into this Google form, they are sent into Lightning AI, and
okay.
we got information
So we can, all right. So the Lightning AI has some sort of credits, and you get some for signing up, and I basically bought more if you didn't get them for signing up or if you used it before or whatnot. So just make sure that you have the credits. It should last for the exercise, and if you don't have, then let us know, or let me and Marek know, and we'll basically add you to this space. I can try to see. So I guess right now there is just us, but we can add you for credits, and then just make sure that you do the space, and when this works, what you should see is basically. You should have a list of basically virtual machines that you can fire up with the code, with the data, and with the GPU. So it should be everything you need to basically to do the exercise from your laptop without having to worry too much about infrastructure. So I'll start this just to show you how it looks like. And you should get your personal one if you follow the badge in the repository. And then on the interface, you see here on the right, you can switch from a CPU to a GPU instance. The L4 is okay for the exercise. So this is the first thing to do. It should spin up in a moment. And otherwise, there is the code. There is the README has instructions on how to start. And I would say that the first exercise, which is basically you download the pre-trained model. By the way, training the model takes about 5 minutes. We have 2 data sets. One is Tiny Shakespeare, because this is what we forked it from. The other one is, of course, Schweik, because we are in Czech. So if you want to play with the Czech language, there is a setup to train a Tiny Schweik language model. So under configuration, there should be, yes, train a fake character model, and then this will speak Czech to you. But the basic one is in English, so you can download it, you can try to sample from it, and you will see the effect of basically the small field of view of the transformer. So it generates something fairly meaningful for the first 200 characters, and then it breaks down, and the first task is to fix it however you want. And the best way to fix it is basically to make it a rolling window. So rather than take a model trained on the history of 200 and then fed more than 200, just constrain it, which you can basically do editing the sampling code in the model pie. So maybe I'll show you roughly where this should go, right? The model has a okay. So you can switch to the GPU instance and show you how it looks like. So go away. So we have the generate, and basically there is a state or the KV cache, which is basically looped throughout the system, and the best way is to go there and just clip stuff, so do a rolling window. To fix the, you can do it here or you can do it where it's created. And then for the other exercises, the one which is, I guess, doable today, maybe if you work a little bit, is to try to change the attention to do linear one instead of softmax. So we provide you with an implementation of the attention, which is basically this naive attention which does everything by hand. There is a softmax here. You would need to remove it. You would need to add some normalization, so the instructions are there. It won't work as well as the softmax because it's a very small model. Basically, you will reduce the memory significantly, but it will start to work and give you basically some hope of doing, if you scale this up, it will work like a state space model. So I would say that in the time frame that we have, fixing the window and then trying to change the transformer into a barely working state space model, just to see the light in the tunnel, would be enough. And for now, if you download everything, this is what you should see when you do the sampling on a GPU machine. So hopefully this will work for every one of you. And as you see, it starts with something which looks like English, the 4 hashes are the starting token, and then at some point it starts to generate garbage. And the first task is basically to get rid of this garbage by playing with constraining the KV cache, so doing a very simple management. And me and Marek basically will, right now, let's say that you raise your hand if you run into problems, and we'll be roaming the room and trying to help you out with this. So all the problems from sign up to lack of credits to you don't know how to get started, make the best use of me and Marek for this part. And I'll try this tiny fake just to see how it works. You can clip time, so let's say you select the last 10 guys. And you have to do the same for the values. And this changes your ever-growing KV cache to the last 10, which obviously will not work super well. But you have to sort of try to clip it to where the models start to go off the rails. And the better solution, of course, is to train with a larger one or do something else. But this would be the first attempt to do it. So you go to model, and we tried to squeeze all of the model into basically one file that is somewhat easy to read, such that there is no magic. But unfortunately, it's still 200 lines of Python. Anyway. So the starting point would be here. It improved? Yeah, there you go. So of course it's cheating really, right? Because it's not really using all of it, but it's the first step that you could do. Now you can try to see whether you are able to train it with a longer one or do anything else. And yes, and if you want to do the internship, this is a QR code for later. Najlepiej z tym internshipem, żeby się koledzy... No, I have to show my company, I did some. Exactly.
You need to like, yeah, exactly. Kamera cię kocha. To ja jeszcze tutaj z perspektywą. Yeah, I mean, like with the sandals and now the American shot. The American shot is the professional. Oh man.
Thanks, Marek. Okay, thank you.
Okay, well, thank you very much. Thank you. Any final questions or comments? You can also do them on the
So yeah, we'll stay here for a moment. So if you want to chat, grab us. If you have any final questions, then this. I heard that someone did the exercise, the first one, and it worked. So there is hope. All right, then. Thank you so much, and thank you, Honza, for the invitation.